Now let's take a look at the second type of the static indeterminate problems. The second type is featured by over-constraint like this. The top and the bottom are both constrained, and here we have a load applied, and as one example here. So this problem can be solved by two methods, and here this is a method one. In method one is this: we add the two constraints. Definitely we know the reactions, and we place the constraint by two unknown reactions, RA and RB. The both are unknown to be solved. And then we take the Freebody diagrams in the sections where the sections basically kind of separated by this loading. So the strategy, the thinking is this: in the upper portion here, we take the cross section, which is very close to the loading position but not included. Okay, that is the strategy. So for this Freebody diagram, you can see due to the action reaction, this is a force RA. Okay, and in the similar fashions here in this lower portion, they take the Freebody diagram, and again we take the section that is very close to where the loading applied but not included. So that is where here. So because the P is not included, so that's the Freebody diagram, and due to action reaction, this is RB. Okay, so now by looking at the so that is a Freebody diagram. So by looking at the equilibrium equations from this side, the two unknowns in the vertical displacement in the vertical direction, that must be equal to the loading applied. So that is equation 1. Then the second equation is this. Here we take this section is in limit, basically in limit to the positions of this point. So basically this length has 0.05 meters. Okay, so that is fitted into our the template. So basically our template is data equal to PL over EA. Using this template, we have PL over EA, and then here we can determine is deformation, and due to this loading direction, the deformation is increased. Okay, on the other side, for this case, again put into this template PL over EA, PL over EA, then this one is decreased. Okay, so this is decreased information. So the amount in increasing in this Freebody diagram should be equal to the amount of decreasing deformation in this Freebody diagram. So in magnitude, they must be equal. In magnitude, they must be equal. So from here, you can obtain this is the second equation here. Okay. So two second equations, then to solve for unknown, we can have RA and RB to solve. So that is the first approach. The second approach is what I preferred. Then this second approach is this. Here we have two constraints, and you pick one, and you simply pick one. And pick one is here I pick B, and you replaced the constraint at B by a reaction, okay, as well as you set a requirement deformation at B equal to 0. Okay, so here is two steps. The step one is to replace the constraint by reaction. The step two is to recognize, because this constraint here, this end doesn't move, so we set up the displacement equal to 0. Two steps. So this is the essence of this method. Then in the step 3, we're looking at these diagrams. Okay, this diagram have two loadings. One is a given, one is unknown. We decompose the loading conditions into two subsystems. Each system is under one loading, and this is a subsystem 1. They only have the loading given loading. This is a subsystem 2 and substitute this unknown loading. Okay, now we calculate individually the deformation for each subsystem. For this system, can you see the delta P that is contributed by the upper portion only? For example, the lower portion here, okay, the lower portion, if you would take any Freebody diagram on the lower portions, okay, this section basically anywhere in the lower portion, you can see there's no loading. Basically, the second portion here, the lower portion basically has the 0 deformations. So in this case, you can see delta P is totally attributed to the upper portion here. For the upper portion, I can draw the Freebody diagram here. So this is a loading P, and due to action reaction, this is a loading P. So the deformation, we can calculate it, that is delta P equal to taking this template PL over EA. And here this L equal to here 0.05. So PL over EA. So that is delta P here being calculated by this. Okay, and this one is 1.5 millimeter downward. Now we're looking at the second subsystem. For the second subsystem, we calculate delta R. Delta R simply equal to PL over EA. P is the unknown loading. Okay, that is the loading. L is right now the whole length is 0.15 and divided by EA. Okay, and now because in the original problem statement, B must be fixed. So in the two superposed systems, they superposed together, delta P in magnitude must be equal to delta R to maintain the original NB unmoved. Okay, so the net displacement at NB should be equal to, for example, you can set up the magnitude equal, or if you like, you can add it up together. So downward, for example, if you take the sign and say sign convention, if you say the downward is positive sign convention, and so therefore upward you can say negative. So if you want to take the sign as well, then the whole together the sign is minus, this is 1.5 and minus delta R equal to 0. So that is here the sign has been included. Otherwise, you simply say in magnitude, the delta P must be equal to delta R in magnitude. I think this will be easier. Okay, so this approach you can solve for RB equal to 3 P over 3. So once RB is solved, then again you take the equilibrium equations, then you can solve for RA. I prefer this approach, but really up to you. Okay. Let us look at one practical examples here. So here we want to determine the reactions at A and B here. So let us take the second method as the solution strategy. And I pick B to release the constraint B by the unknown reactions. And also I set the displacement at and B equal to 0. So basically that is to take up the preferred to here we take the step 1 and step 2. Okay, and now we decompose the system into two subsystems. One subsystem is under given loading, the second subsystem is under reaction loading, and now we individually calculate this loading. Okay, so the deformation delta L is the deformation due to given loading, and then this one being elongated. Then here, because we know that delta must be equal to 0 at the original problem, so whatever this subsystem is being elongated must be pushed back by reaction RB to maintain the end no movement. So that is the thinking process. Okay, so that is the thinking you can look at here. So we can individually calculate for this subsystem that is under loading. We can repeat the previous calculation steps. And so for example, say for this system, let me draw this one here. So that is the system, and this is the loading 300 kilonewton. This is 600 kilonewtons. So if you draw these whole things here, this is the load, okay, and kilonewton, and this is positions. Okay, so in here you should be able to see in these portions the loading equal to 0, and then in this segment the loading equal to 600. Okay, so this is 600, and in this segment the same 600, and in the final portion that is 900. So that's the loading. So for each segment, and say segment, and for each segment here 1, 2, 3, and 4, repeating the previous calculation template. For each segment that has the template is PL over EA. So here you have determined this is the segment 1, 2, 3, and 4. For each segment you have determined the loading, and for each segment you know the geometries. Okay, so we know this one, and for each segment you know the A, okay, and for each segment you know the L. So of course, and we are given the Young's modulus, so you should be able to determine the overall the deformation, and that is contributed by 4 segments, so something like this one. So plugging everything calculated the data L, this number equal to 5.6 millimeter. Okay, now we come to the second subsystem. Subsystem is due to RB here. Okay, so for RB the same thing. In the segment 1 and segment 2, the reactions is always minus RB, the compressive. The minus means compressive, and you know the sections, and you know the geometry and dimensions. So delta R equal to this one, and again this minus simply indicating that's compressive. So basically here the themes is we see next page. So the themes is this. From the first one we've been calculated 5.6 millimeters. Because this is an imaginary deformation, in reality this end must be maintained unmoved. So the purpose of the reaction is to push back. RB is to push back this imaginary deformation back to his unmoved position. So that means the RB must be pushed back by the same amount, 5.6. Okay, so in this way that we have this statement. And again, this one is you can think about in this. For the first subsystem, due to loading, if there would be no constraint, the lower end is free to deform by 5.6 millimeter. However, because in reality we have the constraint here, so such a free deformation is not allowed. And instead, because it's not allowed, the reaction force exists there. So in our model, the reaction force played a role in pushing back this not allowed deformation by the same amount to maintain the constraint, to maintain the end there. So the reaction force, the role of the reaction force is to push back by the same amount to maintain. Okay, so that is a formulation of this equation here. So from here you can solve for RB equal to this, and then using equilibrium equation in the vertical direction, the RA plus RB equal to 900, then you can determine RA. Okay, so that is the solution for this. And a similar, very identical example is here. Simply the arrangement of this problem is in horizontal directions. You can exercise, and that is the solution here for your reference.